Thank you so much for agreeing to present. Today we will hear a nice tutorial from Nick Smith from Fermilab, who is active developer. I mean, he's one of the main developers of Coffee Framework, and he will share a bit his experience of working with Dask, implementing because he was one of the main contributors of actually Dask executor for Coffee. Yeah, so please, Nick, your stage now.
So yeah, basically my goal here is to give you an overview of what Dask is and how I view its place in the ecosystem. And then I'll work through an abridged version of a notebook-based tutorial that is geared towards generic data science users, just based on a tutorial that Dask authors have put forth in various venues. And then I'll have a notebook-based tutorial on more HEP-specific considerations, basically working through an example of processing some CMS open data with the usual uproot, awkward, hist package libraries in concert with Dask. So while I go through this first set of slides, if you would like to follow along with the tutorial, you can click this GitHub link. It's also in the agenda, and there is some brief but hopefully sufficient instructions to get you set up with an environment that you can follow along. You have either the option of using Conda, making a Conda environment, or using a Docker container. Conda may be a little bit nicer, but I think I worked with the Docker container version of this, and it works all right, just not quite as well because, well, Docker. And yeah, like I said, this is an abridged version of a quite polished tutorial that has probably about maybe 6 hours of content, and you can actually watch a YouTube video for almost all of it. It's a 4-hour video and goes through most of the notebooks in the tutorial and gives you a pretty comprehensive overview. Of course, I can't get through all that material, so I'll try my best to touch on highlights from it that I've distilled into a smaller set of notebooks, and then go through the HEP examples. So yeah, if you like to follow along, go ahead and start creating your Conda environment, and then I'll go through these slides while the packages download. So what is Dask? In the author's own words, it's a parallel computing library that scales existing Python ecosystem. And it is essentially composed of basically 2 tiers. There is high-level collections, which is mostly implemented in the Dask named library itself. That includes things like the array, bag, and data frame collections, which are sort of distributed analogs to NumPy arrays, generic lists of objects, of Python objects, and then pandas data frames. And the idea is that they can operate on data sets that wouldn't fit in memory on a single node, on a single machine. We'll go through each of these 3 briefly in one of the notebooks to kind of demonstrate what features they offer and what features they don't offer. And then below that, there is the low-level schedulers. Dask provides a very open interface. It's definitely took the Pythonic nothing is private approach very seriously, and exposes a lot of inner workings that you can use to sort of recreate your own distributed tasks. And it provides these task schedulers to help execute the task graphs efficiently and optimize them. And so, yeah, the schedulers are designed to be very low latency, so that they focus on being able to dispatch tasks to workers in you know, so sort of the 1 to, well, I guess in this case they claim 1,000 tasks per second, but actually in some of the literature they claim they can execute more like 5,000 tasks per second on a scheduler. And they're working to basically improve that throughput continuously. They also pay very close attention to the memory footprint on the workers. So all the task input and outputs, all the data objects that the result features hold have a known size to Dask, and it keeps track of those and decides to spill results to scratch disks or simply delete them if it knows how to recreate them to save memory in ongoing computations. And then basically the distributed scheduler is, you know, an alternative also to using more traditional multiprocessing or multi-threading libraries. And I'll touch a bit on some of these libraries, I think, in actually 2 slides. Feel free to ask questions at any time, of course. Certainly during the tutorial, I hope it becomes a bit interactive, but feel free to talk now. About the ecosystem, of course, you've probably all, being in, you know, PyHEP enthusiasts, you've probably seen this plot many times, and you'll see that Dask has placed itself on this onion of abstractions quite low, you know, on the same level as, say, NumPy or Jupyter, because it is supposed to provide the multi-machine, you know, multi-core scaling solution for these libraries at the upper tier. And indeed it does. For example, scikit-learn, you can use its, it has a sort of native solution called joblib for CPU bound parallelism on a single machine, but you can, with one line, change scikit-learn's parallelism to use Dask instead. So alternatives, it was interesting putting this slide together because I'm almost sure I haven't listed all of them. The market is rich, but I thought at least these are worth mentioning here. Of course, the elephant in the room is Apache Spark, which is actually written in Scala and Java with Python bindings. So Python is not really a first-class citizen in Apache Spark. I think this has been made clear over time, although it does have a very large community and it's well established in industry. I will say, from a personal perspective, we've moved away from Spark towards Dask because unlike Spark, Dask does, you know, provide these more public interfaces for its low-level features, which allows us to tweak it just enough to make it more suitable to our needs than we could with Spark. We reached some barriers with Spark that were difficult to overcome without making direct pull requests to the project, which were actually denied, unfortunately. And I'll also say, from a systems administrator point of view, it's actually much easier to spin up a Dask cluster than a Spark cluster. Joblib is sort of this native CPU-bound scaling solution for scikit-learn. As I understand, it's mainly common in that community. There may be other communities that use it. Celery is an interesting project. It's a task queue that sort of leverages these modern distributed foundations that are, you know, at this point, sort of language agnostic, right? RabbitMQ or any of the other message queues like ZeroMQ are, at this point, have bindings for every language that people use. Redis, you know, distributed caching. And so Celery basically leverages those to their maximum to provide, you know, a generic task queue for work. And it's an interesting project that actually gets used in some places at a higher level, say with Apache Airflow. Scoop is an interesting sort of library that someone had just mentioned to me once that they found very useful, and it was very easy for them to set up a multi-machine cluster and execute some DAGs. Of course, there's concurrent.futures, which really is a protocol in some sense, right? There's a PEP about the futures protocol that many of these other packages actually provide an interface for, including Dask. Ray is an interesting project because it seems to be going in the direction of Spark, but with a Python base. Some interesting facts about it is it does have a multi-scheduler design. Dask has a single scheduler. So in some sense, it's a bit more distributed because Dask only has multiple replicas of workers in a single scheduler. It seems to be geared initially towards distributed machine learning tasks. A lot of the sort of batteries included parts of Ray are geared towards distributed machine learning. But I suspect as it matures, it may start to have some of the same data processing and data frame features as Dask. So it'll be interesting to watch and see how that turns out. Parcel is another Python library that sort of allows you to generically create delayed processing and task graphs, and it seems to be popular in academic and high performance computing communities. And then there's these higher level libraries like Apache Airflow or Luigi, which are also both Python based libraries for executing DAGs. But I think their idea is that they're executing workflows more on the sort of minute to hour granularity and not so much on the millisecond granularity that Dask is targeting. And in fact, Airflow, for example, can use Dask as an underlying scheduler to execute its tasks even. So many options. It's tough to say if Dask is the right one for your case. It depends what you're doing. More resources. There's actually going to be a summit very soon, I think in 2 weeks, where there's, for the first time, a few contributions from the HEP community, thanks in large part to some of the people working in PyHEP, including Sana and Lucas and Jim and myself, I guess. There's a Birds of a Feather session as well, discussing our needs. So you feel free to join there. Of course, there's pretty thorough documentation for this project. It's a very large project. It has a Stack Overflow tag. It has, of course, a GitHub issue tracker. One thing that is rather pertinent is how to acquire resources in a Dask-friendly way. So basically, how to scale. And I think the options here are really tailored towards, or the options here really depend on what kinds of resources you can access. I think in our environment, we're most commonly exposed to job queuing systems, like Condor or Slurm or other batch systems. And to scale Dask on those, actually, there's a quite nice library called Dask Job Queue. It basically allows you to automate and sort of procedurally generate the job submission scripts and spin up worker nodes that can then connect to your scheduler and execute tasks. And this includes also the ability to do dynamic or adaptive scaling, where the number of workers provisioned for your task depends on basically the complexity of the task or how many work items are in the queue. Some caveats apply for this at certain sites because of, well, mostly for firewall issues. Dask communicates between workers in a full mesh topology, and to do that, it needs to be able to connect to ports on worker machines in a cluster. And some clusters have firewalled away the workers from being able to talk to each other. We've actually worked a bit with Fermilab's LHC Physics Center cluster and CERN LX Plus to remove this restriction so that we can test out Dask. And you can see the link here for some more details on how to use Dask job queue at these sites if you want to try it. Coffee Kaza is an interesting project where it's trying to provide an analysis facility in a box where it uses Jupyter Hub and Kubernetes and then HD Condor again to provision the workers. But this may be an interesting project to follow if you're a systems administrator or you want to provide some sort of Dask enabled computing facility. This is a prime example of doing that. So with that, I guess we can turn over to the tutorial unless there's any questions on these slides. Oh, and if people are raising their hand, I don't have that up. I should probably have that up.
No one is currently raising their hand.
Okay.
So go ahead.
We will help you in case to tell you when somebody is asking something.
Okay, sounds good. Well, in that case, maybe we can turn over to the actual tutorial now. Hopefully the installation instructions worked well for those that tried it. If they didn't, please speak up now and say if you had any particular issue. There may be a chance I can fix it with a sentence, but there may also be a chance that I can't. Okay, then I'll go ahead. Yeah, so this is basically distilled version of, like I said before, there's some of the tutorial documentation on the Dask site. The idea here is to introduce Dask delayed, which is the sort of primitive wrapper for providing lazy computation in Python. And it's a very easy way to build up complex systems from small functions, small parts. And we'll see that in use later in the HEP tutorial. So there's a bunch of documentation here. So before we start using these delayed objects, we have to start a scheduler. And sorry, my cat's yelling. As discussed in more detail in this distributed scheduler notebook, Dask does have more than one schedulers built into it. Although for the most part, you'll only interact with the distributed scheduler because that's the one that you would use in a multi-machine scale. So you might as well learn to use that one even if you're running on a single machine, just because you'll be more familiar with its features and idiosyncrasies. The distributed system is basically a centralized scheduler in one or more worker processes, and you can deploy these schedulers and workers in quite many different ways. Like I mentioned in the slides, you can use Dask job queue to provision these scheduler and worker processes on a batch system like Condor. But you can also even just open up a terminal and just type Dask/worker and Dask/scheduler. And as long as you just wire them up together, you tell the worker the scheduler's IP address, then it's all ready to go. You can even just take two laptops on a desk and fire up a worker on one and a scheduler on the other, and you're ready, multi-machine. Doing things locally is very convenient because if I simply just instantiate the client here, what I'm actually getting is a Dask client that is running in my process. And then it spawns also a scheduler process by forking, and then also spawns 4 worker processes by forking. So there are actually now 5 processes in this notebook. There's the client, the scheduler, and the 4 workers. And each worker is by default here configured to use 2 cores because I have an 8-core machine, and then it's decided to allow itself to use the entirety of the machine's memory for better or worse. But of course, if you want to restrict that, you might consider adding a memory argument here, which you can do. Okay, so that's the whirlwind introduction to the scheduler. There's also a dashboard that we'll get into in more detail later, but it looks very nice. And yeah, let's get back to that later. Okay, so let's make some toy functions, one that adds one to a number and one that adds two numbers together. And we've added gratuitous amounts of sleep so that we can actually observe the delays that are caused by these functions. And these are basically to simulate, more expensive CPU bound or IO bound work. And if we time these, we can see, well, we have three sequential operations and each one has, an expected time of 1 second. So the total time to execute this cell is 3 seconds. So that makes sense. Looking at this, you can imagine that you could parallelize it somewhat because the two inputs to Z are independent of each other. So what we can do is we can import this Dask delayed function, which is sort of a higher level functional object, right? You can wrap another function with delayed and you get a new function out. And by calling that, we've actually created a task graph. You can see that the total time here is in microseconds, and that's because no actual computation work has been done yet. But we can then trigger the computation here, and in theory, you should see that it's faster. So yeah, it only took 2 seconds. So the Z object itself is this delayed object. It has, some token that uniquely identifies it, and it knows, what it needs to compute the result. And you can actually visualize the task graph that it's constructed with this visualize feature. And you can see, it's recognized that the two increment calls are parallelizable, and so it's running those together and then adding the results. So, I think hopefully it's clear why it went from 3 to 2 seconds, and why weren't we able to parallelize to 1 second? Well, the add is a second level in this DAG, so there's really no possibility. And here's, if these functions didn't include the sleep, would this be able to speed up the code? Marginally, right? Because now your actual operations are so tiny compared to the scheduling overhead that most likely it will actually take longer. But that's kind of it's an interesting point, right? Is you need to split your tasks just to find enough granularity that the task work time is small, so that you get the the benefits of granularity and task graph optimization, but large enough that you aren't in the regime where the scheduling overhead is significant. You need to stay, you want tasks that take order 1 second or longer, basically, I think is the general order of magnitude. So let's try something a little fancier here. Let's parallelize this for loop. So what's happening here is we're taking a set of input data, we're incrementing each value and then appending some results and then creating a sum. And if I run this, it's going to take 8 seconds because there's 8 items and it has to increment each 8. So then there's a little exercise here where you can try to parallelize it yourself. I'm a little worried about time already, so I might leave this as a homework item for those of you that are following along. But the conclusion basically is that you can parallelize this, quite extensively because each of these are independent, and then sum them. And you should see, if you do it right, a wall time of 1 second. Now, one caveat is that suppose you have some more complicated expression where there's some control flow, right? Maybe you double a number if it's even, or you increment it if it's odd, and then you append the results. So this is a bit, harder to parallelize because what you do depends on the control flow. Again, there's a homework item here, and I encourage you to try it. But without peeking at the answer, we can still look at its performance. You can see it went from 10 seconds to 2 seconds. And if we look at the task graph, you can see that, various items are doing different tasks, basically if it's even, you're doubling it, or if it's odd, you're incrementing, and then you collect all of them at once. So all of these run in parallel, and then you have the sum. But the initial, decision to make these, right? That is not something we could put in our task graph because it was, it's a higher level than that. Okay. So there are a lot of examples of control flow where you can't use delayed. You have to materialize your result and then act on it. Now, if you get fancy, you can include these materializations in the task graph. In fact, Dask can spawn tasks from tasks, but you should probably consider that sort of an advanced feature and specific to strange corner cases where you really need to spawn a task from a task. Generally, I think it's better to construct the graph as complete as possible so that you can let Dask graph optimization routines improve it. Okay, I wanted to spend a little bit on features because it's sort of an important piece of the low-level part of Dask. The clients provide this concurrent features like interface where you can submit or map and wait and all of those usual concurrent features functions. And you can think of these as just the eager equivalents to the delayed functionality. And it just allows you finer controls of exactly when tasks are submitted. So if you don't actually want to construct this task graph, if you really want to tell the scheduler yourself, execute this function now, execute this function now, you can do that with the submit. So for example, right now I explicitly told the cluster, please run increment with this input. And so it returns this future. And if I want to get the result from the future, that takes the value back from the cluster and returns it to my local client process. And any delayed object can be turned into a feature just by telling it that we don't actually want the result. We just want a feature that holds the result. And so in this case, I'm using the same delayed increment call from before, but computing it with that option. And sure enough, the result is the same. One thing to keep in mind if you are using features, it's an important gotcha, is that the feature object itself is going to hold a reference to the result. So if your result is particularly large, or if you have a lot of them, you need to make sure you manage your references carefully. And that, that basically boils down to making sure that you, delete your future. And if you're working in Jupyter or Python, you need to keep in mind the sort of magic references. So you need to do things like that. Right? So this is one reason why, working with features might not be, so advisable in some cases, because then you have to worry about reference tracking and stuff like that. So something to keep in mind. I see there's an item in chat. Oh, yeah. Yeah, this is just a general PSA for Jupyter notebooks is remember your magic references if you're trying to dig out why you have so much memory usage. Okay, calls to compute on delayed objects can pass additional arguments, and those are just forwarded to the actual executor's compute call, which is a slightly different signature and has many more options, including things like automatic retries or binding computations to workers with resources. And this is a good way to, if you have a cluster where only a few nodes have a GPU, you can tell some portion of the task graph that it can only execute on nodes that have the GPU. And the rest of, and the scheduler will know to put those tasks there. So here what I've done is I've implemented a unreliable increment operation where basically half the time it just fails to do its job and raises an exception. So if I run this with pretty good, with coin flip odds, it's going to fail. So let's see how often I have to, there you go. So it died. If I want to make this more robust, I can just add some number of retries, let's say 3, and hopefully with enough reiterations of this cell, I can convince you that it errors less often. Of course, it's probabilistic, so I'll have to take my word for it that it is actually retrying the computation. Okay, so if you want to learn more, there's some documentation and some screencasts, and pay attention to the best practices. I think they're really nice, and they summarize some of the caveats. So yeah, that's it for sort of the low-level features of Dask. Any questions? Okay, well, I'll go on to collections then. Just clear the output. So again, I'll just set up a client on my local machine. And then I'll introduce some of these. So bag is sort of a generic, so bag in CS parlance is basically, it's an unordered list. So it's something where there can be duplicates, but the order doesn't matter, and the order doesn't matter. It's just a bunch of stuff that you need to process. And so it's good for processing, sort of a sequence of arbitrary inputs, which is, some messy object. Maybe it's JSON, maybe it's, something that's not nice to process. And you can think of it just as, some combination of the Python functional style of stream processing, where you use map, filter, reduce, and some of the fancier functional tools. So to play with it, I'll just make a little random data set. And this is, again, just taken from some of the Dask documentation. They make a directory. They have some built-in function that makes random data, and then we dump it to a set of text files. So now we have 10 JSON files that add up to something like 3 megabytes. But you can imagine, in a real world situation, you might have a Hadoop file system with a few terabytes of JSON, and you have a cluster of, say, 100 nodes that can load and process this. And then in that case, bag may be a good choice. So one thing to notice here is we can use these sort of glob expressions in the read, and this applies to both bag and data frame and many of the other high-level collections. This also, in principle, can take URLs and URLs with globs if the protocol supports sort of directory listings. So things like S3 or HDFS URLs can actually still use glob, which is quite interesting. Xroot D eventually. All we need to do is write actually an Xroot D file system spec, and then we can do that with Xroot D. So if someone wants to volunteer, please do. I'll get to it eventually, otherwise. So if I want to take one element from this, I can just take the first one, and you can see it's just a sort of a contacts listing, age, name, occupation, and it has some rather undesirable features, like the name is split by space, or the address is a nested structure. So you might imagine that this wouldn't be so easy to use in a pandas data frame directly. You might have to first do some transformations to flatten or filter these. So here's an example of filtering basically all the records for age over 30. Here's one where you're just projecting one element of the record. And then I'm just taking the first 2 results, or just counting the total number. You can see there's not so many. And you can chain all these together, just like with delayed, you can chain subsequent reductions and projections together to sort of create this task graph for the bag, and we can actually visualize what this looks like. You can see it's taking actually all 10 files, parallelizing the bag transformation, the filter, and then sort of aggregating the frequencies into one single result. And you can compute it, and you can find out that looks like building engineer is the most common profession in this data set. So that's all I really wanted to say about bag, just in interest of time. Arrays, basically these are n-dimensional flat arrays, so distributed NumPy. You can use, all the cores on your computer, or, have active, in-memory workloads larger than, a single machine's memory footprint, say, even up to order terabytes if you have enough workers. And you can do sort of large computations as long as there's some sort of parallelized block algorithm for the computation. So in this example, what I'm doing is I'm just creating this 20,000 by 20,000 array of random numbers. And you can see the total array size is 3 gigabytes, but each chunk is only, a few megabytes. And we can parallelize things like taking the mean over an axis. And again, this is all delayed, right? We haven't actually computed anything when we executed this. But we can if we just call the .compute on it. And this is, took 2.6 seconds on my machine, which is, I think, is pretty impressive considering it's a 3 gigabyte array. And at no point in time was that array actually, like fully materialized in its contiguous form. So there's sort of a performance comparison from the authors of this tutorial, and you can see that actually my machine is faster than theirs. I assume that's just because it's newer. But you can see that, yeah, if you did this with NumPy, which you can if your machine has enough memory, 4 gigs is not an unreasonable amount of memory for a single machine. Even then, it would still actually be slower. And that's simply just because we're parallelizing some operation. Of course, the total time, right? The time, the CPU seconds is actually lower for NumPy, and that's sort of representing the fact that there is, as always, there is scheduling overhead. That you can see here actually that the scheduling overhead I see. Oh, right, because I'm using a distributed scheduler, so you can actually see the scheduling overhead. Okay. Yeah, so if we chunked it finer, would it still be as fast? Probably not. Then you're starting to get into the scheduling overhead regime. Would we use less memory? Likely, but it's slower. If we lower the amount of chunks, you can play with that. You'll see, basically the inverse. You'll have more memory footprint at any given time, but the CPU time, the total time may be lower. Now, there are many built-in algorithms that are probably useful for your case. Like if you want to do SVD, singular value decomposition on a huge array, you can do that. It will try to parallelize it as best it can, although there are some limitations. There's a compressed version of it that's sort of stochastic and can operate on even larger arrays at the expense of only being an approximate result. And there's other sort of matrix algebra functions like that are built in. And it certainly doesn't implement the entire NumPy interface, just because, well, the NumPy interface is huge and there's only certain, basically it implements things that people that work with Dask needed at some point. It's very user contributed. So at some point someone said, we really need to do an SVD, which isn't just surprising. That's a very popular thing to do in, data analysis. but you might not find every single, linear algebra thing. Like for example, eigenvalues of, Hermitian matrix that you would get in NumPy. It's not there. But nevertheless, there's a lot to get, your feet wet. And if there is some parallel operation that you know of that isn't implemented, of course, you could go and implement it. Sort. Now, I think this is actually outdated because there is some sorting functionality both in the array and data frame, but it's a bit limited because, of course, sorting requires shuffling, which is very expensive. So, yeah, that's all I'll say for array, just for sake of time. Data frames. This is sort of, pandas. Think about pandas. It's great for data sets that fit in memory. You should not use Dask data frames if your data set fits in memory, just end of story. It will be faster in pandas. But if your data set does not fit in memory, or if you have to load it, in a distributed way, which is usually the case, right? If you're IO bound, even if you're IO bound, having multiple machines helps, right? Because it can basically increase the number of, clients to the distributed file system. So of course, for the data set that we're working with, it's completely inappropriate, but you can imagine, how it would scale. And basically, it's implemented just by blocking a pandas, a contiguous data frame along the index dimension into manageable chunks. And of course, it's important to size these chunks appropriately. And you can tune that yourself by adjusting the partitioning. So what I'm going to do is I'm going to take the same data set that we were using for a Dask bag and read it into the data frame. And you can see that a lot of the columns are actually object columns, which is usually a no-no for pandas, right? And this is just because this data set is structured. But we can actually fix that pretty easily, right? We can apply along one of the axes, like say the address axis, we can resolve the city. And here I'm actually specifying some metadata to help Dask know what the return type from this function is. Because actually the way that Dask knows that these are, the age is an integer, name is an object, is because it will take the first partition, materialize it, and then check the result. Optionally, if you don't want it to do that, you can actually specify the metadata manually, with, where is it? Meta, yeah. So you can specify the metadata if you know it ahead of time, which prevents it from having to load that first partition. And then for derived columns like this city column, you can easily specify the metadata here. Like I know this is a string, and that will prevent it from having to actually compute anything to add these columns to the array. And with that in hand, we can do some computation. Like let's find the oldest 5 people on our address book. So Marjorie is quite old, but not too old, just past retirement age in the US. These are random generated. You can do things, like aggregate, things like what's the mean age for a given occupation. So accountant is 35, whatever. You get the idea. Just imagine doing this with, a few 100 million or 1 billion records instead of 10,000. So that's all I'll say about collections. Questions? First error, nice. So one thing to know about Dask is you will get, because it's an asynchronous client server interface with several IO loops, there will be cases where a separate thread in your process will have some issue and it will spit out some garbage. Typically you can ignore it. My experience is that it can get noisy when inter-process or inter-machine communication is flaky. So if you have a loaded network or bad connection, you get a few drop packets, you might get a temporary error, which is usually recoverable. It's not something that necessarily kills the computation, but it can be somewhat disconcerting. And I think it's really it's kind of a fact of life unless your cluster is absolutely, immaculate. There are certain knobs you can tune, as a system administrator to, relax the timing constraints, like tell Dask, no, not every machine will respond in your default timeout. Here the timeout is 10 seconds. It's just something to think about and just be aware of and not to get too worried about as long as your computation finishes. So with that, I guess I'll go into the HEP analysis example. So I only have about 10 minutes left, so let's see how we do. So here I'm trying to synthesize the use of the delayed in collections with something more familiar to those of us that work in PyHEP, uproot, awkward, and hist. And we'll build a pretty complex task graph, which is nice. And hopefully I'll be able to use that to spend some time showing you the dashboards. Okay, so one little caveat here is we need to teach Dask about our data types. Oh, that's interesting. Is this because, oh, I think I know why this is. I had not imported awkward yet in this tutorial, so I apologize that I did not remember to fix my environment for that. Should be able to fix that pretty quickly. Fingers crossed. Uh-oh. Okay. Sorry about this. Not sure why it worked the other day. Yes, I know. Is anyone following along and receive the same error, or is it just my environment?
So that error is interesting because it does have a package named awkward installed, but it can't get the compiled part of awkward, which is awkward._ext. I actually don't know how you can get the package without the compiled library within it. So Jacob was following along, didn't get the same error. It has to do with yeah, same thing for Nick. Has something to do with installation and setup of your environment.
Yeah, I think the issue is that in my machine, I have I have it set up to always, read from, some master version of the awkward library. So I have, some Python paths and library paths overridden that I forgot to disable for the tutorial.
Okay.
So apologies for that. I'm trying to fix it.
People who are following along, are you doing it on running Jupyter locally on your own computer or using Binder? Which of those? Because with Binder, I don't think you would hit these issues because of the fresh install. Local Jupyter instance, Nick Marandella.
Okay, you know what I'm going to do? I'm going to switch to my let me switch to another environment. I have one running also on the CMS LPC cluster. And I believe this one works, even if my laptop is messed up. I'm gonna upload. Okay. So with some luck, this will, yep, okay. So now I'm running actually at the Fermilab LPC login node instead of my machine. I still have 8 cores, but I have less memory. Okay, and this actually might be useful for the tutorial because I'll have a better network connection to CERN. Okay, so sorry for that interruption. Right, so we were teaching about our HEP-specific data types, and all that's in this patch is basically just teaching this Dask size of utility, the size of awkward arrays and awkward arrays. I feel like in some future tutorial that won't even be needed because we'll have made a pull request to Dask to know about our objects by default. Okay, so all that aside, we're going to open 20 open data files from CMS data collection 2012. And here what I'm starting to use is delayed as a decorator. Remember, delayed was, you know, a higher order function, so you can actually wrap other functions with it using the decorator syntax. And you can get these what's basically a delayed object that is going to later open this file. And we can compute that and bring it back to our worker and then use the show on it, which is the usual method that you would get on a T-tree. And you can see that for the first input, for the first of these 20 files that I'm reading, this is the data that's available in the root file. So with this information in hand, we can start to create some awkward array structure representing these muons, you know, as Lorentz vectors with a charge. So here I'm using coffee nano events vector just because, well, vector is now in beta, but I haven't tried it and I'm not as familiar with it. So, but I think it's ready already for this kind of use if you want to start using the feature vector library. So what this delayed function here is doing is basically taking the tree, which will be itself a delayed object, in some range of entries just to limit how much data we process at once, grab an array from it, grab a few arrays from it, and build this awkward array. And you know, when handling these large arrays, we need to make sure that the chunks that we generate here, you know, with this tree entry start, entry stop, have appropriate data volumes. We need, you know, we want something, you know, maybe order 1 to 100 megabytes. You saw in the previous tutorials how Dask, you know, the Dask array was sort of the order of 5 to 10 megabytes per chunk, and here we're targeting sort of a similar size, because each individual file is actually over 2 gigabytes, so that would be unwieldy, especially if you have intermediate results that you need to compute. So we set entry ranges, and here is an example, you know, where you have to do some pre-computation. You need to know how many events are in each file. So what I'm doing now actually is I'm querying the number of events from each tree, and you can see I'm actually accessing a delayed object and calling it a get attribute on it. And just by passing this set to dask.compute, I get a list of entries. And it turns out that all the files have the same number of events. So here's a simple algorithm to chunk those into chunks of approximately 400,000 in size, but making sure to chunk it evenly. And so if I do this, I get basically 3,000 chunks, and the first chunk is listed here. So if I want to look at some of this data, I'll probably want to pull one representative chunk down and play with it a little bit. So a nice way to do that is to use the persist function. So it takes these lazy Dask collections and turns them into the same thing, but now with the results fully computed or available and persisted in the cluster. So I do this, I basically rewrite this first delayed object with a persisted copy of it. And then I ask Dask to actually pull that result down. And let me pull up the dashboard for this. And now you can see actually it's processing this graph. We have the get tree, and then we have the muon struct. And if I go over to the task graph, you can see it's a very simple task graph. And now you finally see something that takes some time, because this is slowly pulling data from CERN to Fermilab. And you can see that the worker that this task is running on is slowly having its memory increase. And this task should finish in a few seconds. I think it took something like 30 seconds for me. And basically the entire time here is actually just in the network latency of getting the data and bringing it back. I think the EOS public is rather slow, unfortunately. But this is sort of good for demonstration because we can actually start to investigate some of the diagnostics. For example, if I click on this task processing for the worker, it brings me to this details page for the worker. And you can see what task it's holding in memory, which it's processing. You can also see, for example, the current call stack. You can see here actually where it is in uproot. You see it's trying to turn these baskets to arrays, and it's waiting on another thread to get the IO result back. And if I click on this, you'll see, basically things that it depends on. So it depends on getting the T-tree info and then the dependents that may need it, which are none currently. And then you also have my client, which holds the future. So that goes back to what I was saying about keeping track of when you have future references, is because clients holding futures is important to keep track of. So now it's done. It's in memory. You can see its type is this, this Lorentz vector array, and significantly Dask knows how big it is, thanks to that patch we did. So now we can actually start to play with it. We could make a hist of the number of muons, or make a hist of the invariant mass of dimuon pair, and you see lots of resonances. Oh, sorry, this is almost at the hour. If people would like to continue, feel free. I'll try to make some concluding remarks here before I go into the future. But basically what I do next is I create a task graph where I make delayed versions of constructing each plot. And then I also make a delayed version of creating some sort of data frame out of the information. And then what we do is we engineer it so that Dask has the entire task graph and computes it all at once, and then writes the data frame out to a table. So since it's now 10 o'clock, are there any burning questions for people that can't stay? Actually, I guess I said I wouldn't be able to stay either. Okay. I'm hearing silence, so I'll try to accelerate through this. Sorry for going over time. Sorry for the delay in getting my environment de-scrambled. Okay, so you can take this delayed muons object, create a histogram from it. So here I'm just making a histogram with 6 bins, double storage, and then filling with the number of the items in the muons. And here I'm creating sort of a filter expression where I select awkward array with exactly 2 muons and opposite sign, same flavor. Well, we know it's the same flavor because it's only muons. And here I'm using this sum feature of the Lorentz vector array to create a dimuon candidate. And then finally, here it's supposed to take in that candidate and fill in the plot with its mass. And here I'm actually using kind of a nice feature of histograms. You can have a log regular axis. So if I execute this here, you can see that I'm passing in my delayed object. Remember, muon 0 is just a delayed object. And here I'm nesting several functions that are all delayed and computing that. And you can see how fast that actually computed. It's actually just taking that result, and yeah, there it is. There's the task. There's the mass plot task. There's the. I can actually zoom in here. You can see the tasks that were executed in only a few milliseconds. Okay, so like I said, I wanted to include some pandas data frame. where I'm taking some, taking the filtered muons and the associated candidate that comes from them, and then creating a table with the candidate mass and then the plus and minus muons kinematics. And so this is what it looks like for the first chunk. It's got 150,000 rows. So let's try to scale this up. Let's create a results object where I just create a tuple of each one, and notice that I'm making no attempt to optimize here. I'm not trying to, reuse the filtered candidate like I do in this optimized version below. Yet when I pass it to this visualize, you can see that it recognizes when there's two things that are the same and optimizes the graph to read as a result. So for example, the filtered muons get passed directly to can table, and the dimuon candidate gets passed to can table. So it optimizes the graph if you explicitly construct it. And we can reduce this graph by using the, we'll have this graph for each muon chunk. And there's basically three outputs. There's the mass plot, there's the n muons plot, and there's this candidate table. For the two plots, we basically just want to aggregate them by summing. So we can use the Dask bag fold operation to do the summing. And then for the Dask data frame, we can use the data frame from delayed feature to take each individual pandas data frame, which is again a delayed object, and turn it into a distributed data frame. So that's basically what these lines do. They create its Dask bag. There's a small technicality that you have to go through to make that work. And then we make a table, and then we filter some results. We say we only want things, compatible with the Z. And then we repartition the table. This is rather important, so that we only have 2 files instead of several thousand. For this demo, though, I've only actually, you can see here, I've only actually taken the first 10 chunks. The first 10 chunks of our delayed muons. But if you had a large cluster, in principle, you could remove that restriction and do all 3,000. Now I can visualize what this is doing, and you can see it's a pretty complex task graph now. You can see, each loading the muons, computing some arrays, aggregating them. So here's our 2 histograms, and here's our sort of pandas flow. And we can compute it. So this will take some time, and we can go look at all the things that Dask is doing. So you can see it's basically all the items are currently waiting on muonstruct, because that's the slowest piece of this task graph, is downloading the data from EOS. But some things that you can look at when you're at a dashboard like this, if you click on these objects here individually, you get taken to a profile of them, which actually shows basically a statistical profile of what's happening. And here's how I can sort of prove that this muonstruct is basically entirely in this uproot waiting for results. And over in this tiny section here, you can finally start to see things like decompression. So the decompression is tiny compared to just fetching the data and the assembling of the arrays, almost insignificant. And you can look at some of the other things like the dimuon can. So this has to compute, things like Z and time and X, Y, Z, T, basically turning the polar coordinates into Cartesian coordinates, and you can see how much time each one is taking. But if you look at the overall time here, right, we have, and this is an aggregate time over the entire computation, we have something like 500 milliseconds versus the muonstruct, which is 1,000 seconds. So you can see pretty clearly who's the big time waster here. It's just fetching the data. So that's why it's important to have a speedy analysis facility. Also, the task graph is kind of interesting. It shows you the task state, whether they're in progress or they've been released. So for example, all of these tasks, since they have no unfinished dependence, their memory can be released early. And then if you go to info, you can see the worker info, and you can dig in more deeply into the tasks that are processing, right now it's processing this muon1 struct, and then you can see that it depends on mass plot, and you can chain through these to see, basically the task DAG and what it's doing in the call stack if it's processing, which is really nice to just kind of dig in and understand what's happening in your workflow. And the workers kind of gives you an overview of the CPU and memory usage. You can see that basically we aren't using much any CPU because we're just in IO wait. And yeah, there's just a whole host of diagnostics available here. And you can actually also access them, if you have the Dask Jupyter integration, you can actually paste this dashboard URL into here and basically get the same information, just maybe slightly more convenient in the notebook. If it loads. And I think at the Coffee Casa, you can actually create new clusters with this dialog if you want to, instead of having to instantiate them from the client. And that allows basically to have a cluster that lives longer than a single notebook, which may be useful in some cases. So I'm 10 minutes over. My job is a third of the way done. Oh, there we go. Now it's further. You can see basically as soon as the muon struct computes, everything else computes almost instantly. Some things to know is this gray shaded part represents tasks that are actually submitted and actively processing. This lighter part here represents tasks that have been released. So only this sort of dark shaded one represents tasks that are actually held in the cluster at the moment. And so that's useful to see, if you have a large number of tasks held, that might mean that your graph isn't really very well designed and you have a lot of downstream tasks are waiting on something, and that means it's going to clog up your memory. And you can see that, we're using, pretty low amount of memory so far, and a lot of it is actually unmanaged, which means it's memory that Dask doesn't actually know about. It's things like just the Python modules that are loaded. With any luck, the last task will complete, and then I can sort of finish this. Yeah. I think there's a small unoptimized piece where in the muon struct where I could have made it faster by telling uproot explicitly which branches I wanted to load so that it could create multiple fetch requests in one, which I didn't do. So there is also the speed of light overhead of having to go from Fermilab to CERN and back. I need to check these files. They might have really small basket sizes. Maybe that's why it's so slow. I'll say in my experience for processing, properly optimized input files, that you can start to see that, you can pretty easily see your test time or your actual computation time, be on the same order of magnitude as this sort of reading and decompression. Okay. Finally done. Let's make some plots and call it a day. So now the plot looks much nicer. You have 2 million dimuon events. We have a really beautiful spectrum. You can see all the upsilons and everything. And we can actually look at our Perquet output, which was put in this folder, with the various partitions, and we can load that whole folder in one execution with this pandas operation. And we see we've distilled down to only 300 or 400,000 rows compatible for ZPeak. One last thing is I want to look at the memory usage. Right now, each worker is somewhere around 350 or so megabytes. Let me restart the client, which basically just restarts all the workers. Now they're down to something like 60 megabytes. So what's that about? we didn't have any tasks left in our queue. Why is there so much memory usage? Well, and the answer is basically the way that memory allocations work. The memory is requested from the operating system by the worker processes as a, satisfy peak usage, the most arrays you have in memory at once. And it's not always relinquished immediately. In some cases, it can take a really long time to be relinquished because they basically form memory pools. And if any object is left alive in that pool, it will stick around and prevent the pool from being released back to the operating system. So that's kind of an annoying feature of working with array programming. Things to do to avoid that is to make sure that your computations are well factorized and that you delete intermediate results as early as possible. Putting things in task graph is very helpful for that. So that's why I tried to demonstrate basically making as fine a granularity a task graph as seems reasonable for the use case here. But you'll notice this is very manual, right? We had to do a lot of work to do this. You can imagine that Dask could work with awkward arrays the way it works with NumPy arrays. And this is a possibility that we're looking into. So maybe in the future, this tutorial would have much fewer lines of code. So hopefully this gives you a flavor of what Dask is and gives you a good starting point for playing with it yourself. Please let me know. I'm always interested in hearing others' experience with it. And sorry for going so over. I did not paste this presentation before putting it together, so that's entirely my fault. Okay. Any last questions?
One question from Jim.
Well, not so much a question as a comment, but on this point of integrating awkward array with Dask as a new Dask collection, we now have a funded project moving forward to do that with Anaconda, where Anaconda is where Dask was originally developed. So there's that one point. I was also thinking when you were showing all those examples of deleting already used arrays, rather than the laborious process of remembering which arrays exist and deleting them, I wonder if more of the steps were put into functions, like maybe just write a function and use it once, going out of function scope in Python will delete all references
Right.
that were used in that function. So maybe just wrapping things up in functions might make it easier to ensure that you don't have leftover objects just sitting there doing nothing.
Right, and so that's why I tried to make this very piecewise, right, is so that these functions, compartmentalize. And I guess this is also a reason to use delayed as opposed to futures, is then delayed objects themselves are not going to hold a reference to the result. They're just a key that's used in a task graph. Yeah. And so, only the result that you actually compute and save will be held, in memory as a reference, unless you persist it. But that's a very explicit operation, so you're aware of it.
Yeah, like there's questions actually in the chat.
Yeah, so there's one question, is it preferable to use Dask in multiprocessing? Well, you have to install Dask, so that's one disadvantage. In principle, it will perform very similar for a use case that you would use multiprocessing for, like if you're directly using client.map or client.submit. There, probably you're not really getting any advantage over using Dask. With using Dask. But if you start to use these delayed objects or build these task graphs, then clearly, Dask is providing functionality that the standard library doesn't provide. So then it may be useful.
Other questions? Don't be shy to raise your hand. We're also watching the chat.
I believe everybody is just working on your tutorial, so probably you could say like you're available for the feedback in your repo, Nick.
Yeah, if you want to leave some feedback and make issues or pull requests to the tutorial repo, I'm happy to accept them, of course.
Or discussions.
Or discussions, yeah, that's a good point. You can, I don't know if it's enabled by default, but we can definitely turn on.
Oh, there's one in the chat.
Yeah, so I can discuss this a bit. So actually, it depends. If your object has a reference cycle, then you need to worry about the garbage collection. If your object has no reference cycles, as in if you created a graph of the object's dependencies and found no cycles, that will be deleted immediately. And that's something to pay really close attention to when you're using arrays, is make sure that if you have composite objects that involve arrays, make sure they don't have reference cycles, because then they will get cleaned up as soon as the last reference is decremented. If you do have reference cycles, then you need to start worrying about gc.collect and things like that. And that's a way to force the collection, because it doesn't always happen as often as you'd like. Dask itself actually increases the rate at which this gc.collect is called exactly because of that issue.
Okay, I didn't see any questions, so I think we could stop maybe on this point. Yeah. And thanks, Nick, a lot. I mean, I really like the last tutorial. I think it requires some time, so we'll go through it again, but super cool. Thank you again, and yeah, hope to see more such material in the future. Have a nice day then.